The moon is only 3 days away. It is the one world beyond Earth where humans have truly set foot. More than 50 years ago, we left footprints on its surface. And even now, those marks remain untouched in the dust, preserved exactly as they were, because nothing on the moon ever disturbs them. There is no wind, no rain, no erosion to erase the past. That may sound poetic at first, but the meaning beneath it is far less gentle. It means there is no air, no weather, no magnetic field, no protection of any kind between your body and the vacuum of space. The surface shifts between extremes, reaching around 260 degrees Fahrenheit in sunlight and falling to nearly 300 degrees below zero in shadow. The dust itself is formed from shattered glass, electrically charged, clinging to everything it comes into contact with. And yet, we are planning to return and remain there. Step outside tonight and look up at the sky. If the air is clear and the moment is right, you will see the moon without any telescope, without binoculars, without any tool at all. It is simply there, a bright and familiar disk suspended in the dark, close enough that your eyes can trace its surface. Those grey regions, that bright feature near the lower edge is a crater, surrounded by long streaks of ejected material, stretching across hundreds of miles of terrain. All of this is visible from your own backyard. No other world offers this kind of quiet intimacy. Mars appears only as a faint reddish point. Jupiter shines brightly but reveals nothing of its true nature. Saturn, Venus, Mercury all remain distant, abstract lights that require imagination to see as places. The moon is different. It is the only world beyond Earth that truly looks like a destination. You can see its mountains, its crater, its landscape. And there is something about that visibility, something about being able to look up and see another world, that settles deep into the human mind. It creates a feeling that is difficult to shake. The moon begins to feel close. It feels reachable. It even feels safe. That instinct is not entirely wrong. By the standards of space, the moon is close. The average distance between Earth and the moon is about 238,900 miles. Light crosses that distance in just over 1 second. A radio signal sent from Earth reaches the lunar surface almost instantly, faster than a blink. When astronauts spoke with mission control during the Apollo missions, the delay was so small it was barely noticeable. Compare that with Mars, where a single message can take anywhere from several minutes to nearly half an hour depending on planetary alignment. A real conversation becomes impossible. You send a message, and then you wait. Sometimes, as long as an entire episode of television, just to know if it was received. With the moon, communication feels immediate, almost like a phone call. And that difference quietly reshapes how we think about these destinations. Mars feels distant and unfamiliar. The moon feels like a short journey with a reliable connection. The travel time reinforces this perception. Apollo missions reached the moon in about 3 days, roughly 72 hours from launch to lunar orbit. Shorter than many journeys across Earth. A spacecraft leaving on a Monday could be circling the moon by Thursday morning. Mars is entirely different. Reaching it requires about 7 months of continuous travel through deep space. 7 months inside a confined spacecraft, exposed to radiation, enduring muscle loss, bone weakening, and the steady psychological weight of isolation before even arriving, and then the same journey again to return. The moon involves none of that. You launch, you drift through space, and you arrive. The simplicity and brevity of the trip make it feel almost ordinary. More like a short regional flight than a voyage across an ocean. And perhaps the strongest influence of all is this: we have already been there. Between the late 1960s and early 1970s, 12 human beings walked on the moon. They placed flags, drove across its surface, collected samples, and returned safely to Earth. 6 missions landed, and all 6 brought their crews home. No one was lost on the surface. That achievement changed everything. The moon was no longer an unreachable object in the sky. It became a real place, marked by human presence, with footprints, tracks, and instruments left behind, and that shift embedded itself deeply into human memory. The moon became familiar. It became something known. It became the one place in the cosmos where humanity could say, with quiet certainty, "We have been there." And from that familiarity, a subtle but dangerous assumption begins to form. The idea that returning should be simple. The reasoning feels natural. If human beings could reach the moon with the technology of the 1960s, with computers far less powerful than a modern phone, with slide rules, analog systems, and spacecraft assembled with comparatively basic methods, then surely it should be easier today. Technology has advanced beyond recognition. So the conclusion seems obvious. We did it once. We can do it again. And perhaps this time it should even feel routine. This line of thinking quietly shapes how the moon is discussed. It influences media narratives, political language, and the way people are rarely surprised. More often, it is asked, did it take so long? Why did we not go back sooner? The moon occupies a category unlike anything else in space. Mars feels distant and ambitious. Asteroids feel unfamiliar. The moons of Jupiter belong almost to science fiction, but the moon feels overdue. It feels like unfinished work, something left behind that should have already been continued. At first glance, the timeline seems to support that feeling. The final Apollo mission took place in December of 1972, more than 50 years ago. Since that time, no human has traveled beyond low Earth orbit. The International Space Station circles the planet at only a few hundred miles above the surface, while the moon remains nearly 1,000 times farther away. For more than half a century, humanity has remained within a narrow layer of space just above the atmosphere. While the moon sits unchanged, its footprint still waiting. To many, this gap feels difficult to explain. It encourages the belief that the limitation was never technical, only a matter of choice, that we could have returned at any moment if we had simply decided to do so. But hidden within that belief is a deep misunderstanding of what Apollo truly was. The program was never designed for permanence. It was designed for survival, and that distinction changes everything. Every part of Apollo was built around a single objective: deliver humans to the lunar surface, keep them alive for a short period, and bring them safely home. Every engineering decision followed that goal. The missions were intentionally brief. The longest stay on the surface occurred during Apollo 17, when astronauts Eugene Cernan and Harrison Schmitt remained on the moon for about 75 hours, just over 3 days. Even that was considered extended. Earlier missions lasted far less time. Apollo 11, the first landing, spent just over 21 hours on the surface, with only a small portion of that spent outside the lander. A few hours on another world, then back inside, then home again. These were not long explorations, carefully planned, limited excursions designed to minimize risk before anything could go wrong. The astronauts brought everything they needed with them: air, water, power, temperature control. Every element required for survival was contained within systems built to last days, not weeks. They did not construct anything permanent. They did not repair failures in ways that required lasting solutions. Problems did arise, some of them serious. But the response to nearly all of them followed the same pattern: return to the spacecraft and leave. When lunar dust interfered with equipment, the answer was to head back to the lander. When radiation exposure began to increase, the solution was simply to keep the mission short. When a fender broke on the rover during Apollo 17, sending a spray of sharp dust over everything, Eugene Cernan patched it using tape and paper maps. It worked, but only because it needed to last for a few more hours. Nothing about this approach was meant to extend beyond that. None of it was built to scale. Apollo demonstrated that humans could survive on the moon for a limited time. It did not show that humans could remain there for months. It did not prove that machinery could operate reliably in that environment over long durations. It did not confirm that the challenges of dust, temperature extremes, radiation, and vacuum could be managed beyond the short term. What Apollo truly showed though it is rarely described this way, is something far more specific. A human being can stand on the moon just long enough to gather samples and depart before the environment begins to break critical systems. Every success carried a quiet condition. It worked because we did not stay. Over time, that condition faded from memory. What remained were the images: a flag standing in grey soil, a footprint pressed into the dust, astronauts framed against a black sky. These images carry such emotional weight that they obscure the underlying reality. They make the moon appear conquered. They make it seem controlled, familiar, almost domesticated, a place where humans proved they could go, suggesting that returning should be a matter of timing rather than survival. This is the illusion, and it is deeply rooted, to the point that even within the space community, it is sometimes underestimated what returning to the moon truly involves. The idea that the moon is already understood, already solved, continues because Apollo created a sense of completion that was never fully accurate. We went there, we came back, we believe we understand it. So what remains to be concerned about? The answer is everything. Because the moon explored during Apollo missions for a matter of hours is not the same challenge as the moon that modern missions aim to reach for days, weeks, or even longer. And the longer the stay, the less forgiving the environment becomes. Its risks do not remain constant. They grow. Before examining those dangers, it is important to recognize how deeply the moon's apparent closeness shapes our perception, often in ways that lead us to underestimate what it truly is. Distance is not the only factor that makes a destination in space difficult. In many cases, it is not even the most important one. What truly determines danger is what happens to the human body upon arrival, and by that measure, the moon is far from the gentle stepping stone it is often imagined to be. On Earth, distance usually carries a clear meaning. Closer tends to mean safer. If you are lost in a remote landscape, being 5 miles from a road is far better than being 50 miles away. If you are caught at sea during a storm, being 1 mile from shore is far preferable to being 100 miles out. Nearness to safety often is safety. This pattern is so deeply embedded in human thinking that we rarely question it. Closer feels better. Closer feels easier. Closer feels less dangerous. But space does not follow that logic. In space, the risk is not defined by how far you are from home. It is defined by the environment waiting for you at the destination. The journey itself carries danger, from radiation to mechanical failure to the forces involved in launch and return. But the true hostility begins when you arrive, and by that standard, the moon being only 3 days away instead of many months changes almost nothing about how deadly it is to an unprotected human being. The vacuum remains the same whether the journey took days or years. The radiation is unchanged. The dust behaves the same. The temperature extremes remain identical. The moon does not become more forgiving simply because it is closer. It only means the consequences arrive sooner. This creates a subtle but powerful trap. Proximity leads to familiarity. Familiarity creates comfort, and comfort encourages the belief that the destination is manageable. For more than half a century, the moon has existed within that illusion, illuminated by the legacy of Apollo and the memory of 12 astronauts who stood on its surface and returned safely. That perception is reinforced when the moon is compared to Mars. The two are often discussed together, and in that comparison, the moon usually appears to be the easier choice. Mars is farther away. It requires a much longer journey. It has an atmosphere, though one composed mostly of carbon dioxide and far thinner than Earth's. It experiences global dust storms and long communication delays that make real-time control impossible. Against that backdrop, the moon can seem almost simple, a nearby task rather than a distant expedition, a preliminary step before something more ambitious. But this comparison hides a crucial truth. It focuses on distance and logistics rather than on environmental hostility. And when judged by the conditions that affect human survival, the moon is not necessarily the easier world. In certain important ways, it may even be more extreme. Mars, at least, has an atmosphere. It is thin and impossible to breathe, but it is still there. That fragile atmosphere offers a small degree of radiation protection. It generates weather systems that, while harsh, help spread heat and interact with the surface in ways scientists can observe and model. It also slows incoming micrometeoroids through friction, slightly reducing the intensity of impact. The Moon offers none of these advantages. It has no atmosphere at all. Its surface exists in a hard vacuum, fully exposed to every particle, every photon, every micrometeoroid that passes through space. Mars follows a day and night cycle close to 24 hours, not far from Earth's rhythm. The Moon, by contrast, experiences a cycle lasting about 29.5 Earth days. This means roughly 14 days of continuous sunlight, followed by 14 days of deep, freezing darkness. Such a cycle introduces thermal stresses that Mars simply does not impose. Mars has about 38% of Earth's gravity, while the Moon has only around 17%. That difference plays a significant role in human physiology, and its full effects are only beginning to be understood. What we know so far is not especially reassuring. None of this suggests that Mars is easy. It remains an extremely challenging destination. But the instinct to label the Moon as the simpler option hides an important reality. The lunar environment presents its own distinct and severe difficulties, and these do not become easier just because the journey is shorter. The Moon is not a smooth stepping stone. It is more like a surface covered in shattered glass, suspended in vacuum, cycling between intense heat and extreme cold, constantly exposed to radiation that could become lethal to an unprotected human within months. The Artemis program, NASA's current effort to return humans to the Moon, operates within this broader perception. When Artemis was first introduced, the general response was not amazement or concern. It felt more like a quiet expectation, as if this step was overdue. The underlying belief, whether spoken or not, was that returning to the Moon was simply the next logical move, something that should have already happened. Because of this, the program's challenges are often misunderstood. Delays are viewed as administrative failure, rather than genuine technical difficulty. Rising costs are seen as mismanagement instead of reflections of the complexity involved. The common narrative suggests that we should have moved beyond this stage, that the Moon should already feel routine, and that the true ambition lies somewhere further away. By late March of 2026, Artemis 2 is being prepared for its first crewed mission, a flyby of the Moon without landing, expected in April. This will mark the first time humans travel beyond low Earth orbit since the early 1970s. The mission has faced repeated delays. It was initially planned for late 2024, then shifted to 2025, then to early 2026, and later adjusted again within that same year. A hydrogen leak discovered during a fueling test in February pushed the schedule back once again. The first human landing, which was originally planned for Artemis 3, has now been restructured. In a press briefing in February 2026, NASA confirmed that Artemis 3 would no longer include a surface landing. That milestone has been shifted to Artemis 4. The first human footprints on the Moon since Apollo are now expected no earlier than 2027, and many observers believe additional delays are still likely. These setbacks are not a lack of effort. They are a mismatch in expectations. The assumption was that returning to the Moon would be a relatively straightforward engineering task, simply because it had been done before. The reality is far more complex, not because modern technology is lacking, but because the goals themselves have changed. Artemis is not designed to briefly visit the surface and leave. It is designed to remain. It aims to establish a lasting human presence. Plans include sending astronauts to the lunar South Pole, a region never explored during Apollo, where permanently shadowed craters may contain deposits of water, ice. There are also plans to build a small orbital station known as Gateway, along with surface habitats, power infrastructure, and systems for using local resources. Each of these objectives introduces challenges that Apollo never attempted. In an environment where Apollo missions only managed to endure for a limited time, the gap between public expectation and engineering reality comes directly from this quiet misconception. People expect returning to the moon to be manageable because it feels manageable. It is nearby. It is familiar. It is the only distant world that looks like a real place when you glance at the night sky. And so, every delay, every revision, every change in mission structure is often seen as a failure of the program, rather than a reflection of how demanding the destination truly is. There is a phrase that appears often in discussions about lunar exploration. We are going back to the moon. Even the language carries an assumption. Going back suggests returning to somewhere known, revisiting a place already understood, following a path that has already been taken. It carries a sense of comfort. You go back to a place you once lived. You return to somewhere familiar. It feels safe, predictable, expected. But in reality, humanity is not going back to the moon in any meaningful sense. The moon that Artemis aims to explore is not the same moon that Apollo briefly visited. Apollo missions landed near the equator, during daylight, for only a few hours, with no intention of staying. Artemis is targeting the lunar South Pole, where conditions are far more extreme. Light behaves differently there. With the sun remaining low on the horizon, temperatures in permanently shadowed regions fall to levels colder than anything recorded on Earth. The terrain itself remains largely unexplored at human scale. The challenges of operating in this environment are fundamentally different from those faced during Apollo. The thermal conditions are far more extreme. The landscape itself is more dangerous. Lighting becomes a challenge, with the sun remaining low along the horizon, casting long, deep shadows that make movement uncertain and navigation difficult. In some places, the boundary between light and darkness creates temperature differences of hundreds of degrees across just a few meters. Returning to the moon is not truly a return at all. It is a step forward into a challenge that surpasses Apollo in nearly every way. Apollo showed that humans could reach the moon and stand upon it. It did not show that humans could remain there. And the difference between briefly touching a world and truly living on it is not simply a matter of scale. It is something fundamentally different. Still, the illusion remains. The moon rises tonight just as it always has, bright and familiar, unchanged across generations. It appears calm. It appears still. It gives the impression of waiting. It feels like the obvious next step, the one place in the universe where humanity already understands what to expect. But that expectation is about to meet a reality far more severe than it appears. A reality that reshapes what we mean by hostile in the context of space. Because everything that makes the moon feel familiar from hundreds of thousands of miles away disappears the moment you stand on its surface. What replaces it is an environment that challenges human survival in ways few have ever truly considered. To understand this, we begin with a simple question. What does Earth do for you every moment without you ever noticing? Every breath you have ever taken was prepared for you by this planet. Even now, as you follow these words, your lungs draw in air that has been filtered, balanced, and maintained by a system so vast and so reliable that it remains invisible to your awareness. The atmosphere above you extends for tens of kilometers. It carries an immense mass, pressing gently but constantly against your body with a force that has been perfectly stable since the moment you were born. It is so consistent that your mind does not register it at all. You cannot see it. You cannot feel it. You move through it as if it were nothing. And yet, it is everything. It is the most essential life support system you have ever depended on. It does many things at once, all of them critical. It provides oxygen, not randomly, but at a precise balance. Roughly 1/5 of the air is oxygen, mixed with nitrogen and trace gases in proportions that your body depends on. Too much oxygen and your tissues begin to degrade. Too little and your cells cannot survive. This balance is maintained continuously and across the entire surface of the planet, without interruption. Every breath you have taken, and every breath taken by every human before you, has come from this shared system. On the moon, this system does not exist. There is no air, not thin air, not poor quality air, simply none at all. The lunar surface exists in a vacuum so complete that it surpasses many artificial vacuums created in laboratories on Earth. The few molecules that drift above the surface, traces of helium, neon, hydrogen, and argon, are so sparse that scientists do not even classify them as a true atmosphere, but rather as an exosphere. Their total density is on the order of 100 trillion times thinner than the air inside your home. For all practical purposes, there is nothing separating the lunar surface from the vacuum of deep space. The consequences of this are immediate and severe. A human exposed to such a vacuum without protection would lose consciousness in roughly 10 to 15 seconds. As the oxygen already present in the blood is used up with no replacement, what follows is not a quiet fading, but a rapid and violent breakdown of the body, unfolding over seconds rather than minutes. Death would occur within about 1 to 2 minutes if the exposure is not reversed. This is not speculation. It is well established in aerospace medicine, yet even that clinical description does not fully capture how extreme the process is. Decompression in a vacuum is not gentle. It is a direct assault on every system in the body that depends on pressure. The first system to fail is respiration. The lungs, built to function at Earth's surface pressure, can no longer transfer oxygen into the bloodstream. Once external pressure drops to zero, the partial pressure of oxygen inside the alveoli falls below the level required for diffusion. Within moments, the oxygen already dissolved in the blood is consumed by the body's tissues and not replaced. The brain, which uses a disproportionate share of oxygen compared to its size, is affected first. Awareness begins to narrow. Clear thinking disappears. The ability to respond, to reach for emergency systems, to activate a backup, or even to fully understand what is happening, vanishes within those same 10 to 15 seconds. It is barely enough time to recognize that something is wrong. At the same time, the drop in pressure causes gases dissolved in bodily fluids to come out of solution. Nitrogen, which makes up most of the air you breathe and is normally dissolved throughout your body, begins forming bubbles as the pressure falls. These bubbles can lodge in joints, creating intense pain. They can block blood flow in the brain, producing stroke-like effects. They can also form around the spinal cord, leading to paralysis. This is the same basic mechanism that affects deep-sea divers who ascend too quickly, but in this case, the pressure change is far more extreme. It is not a transition from higher pressure to normal atmospheric levels, but from full atmospheric pressure to none at all. Every dissolved gas within the body attempts to escape at the same moment. At the same time, water within the body begins to behave differently. The moisture in the eyes, the saliva on the tongue, and the fluids within exposed tissues start to boil at normal body temperature. This happens because the boiling point of water depends on pressure, and in near vacuum conditions, that threshold drops below 37 degrees Celsius. This is not heat-driven boiling. The body is not burning. Instead, it is experiencing a pressure environment where liquid water naturally turns into vapor. As this occurs, soft tissues begin to swell as vapor forms beneath the skin. Experiments during the early space era, including animal studies, showed that this process unfolds in seconds, not minutes. The body does not slowly shut down in a vacuum. It begins to break apart at a fundamental level. Every second a person spends on the lunar surface, their survival depends entirely on the integrity of their suit or habitat. A single puncture, a failed seal, or a micrometeoroid impact in the wrong place is enough. The boundary between life and vacuum is measured in mere millimeters of material. And yet, the atmosphere does far more than allow us to breathe. It also acts as a powerful shield against radiation, something we rarely consider. Even now, your body is being exposed to cosmic radiation, high-energy particles, originating from distant stellar explosion, from the sun, and from across the galaxy, move through space in every direction. Some travel at speeds approaching that of light. These particles carry enough energy to damage DNA, disrupt molecular structures, and trigger processes that can lead to cancer, neurological decline, and organ failure. They are constantly arriving at Earth in vast numbers. Every second of every day, you do not notice them, because the atmosphere absorbs the majority of this radiation. When these high-energy particles strike the upper layers of the atmosphere, they collide with atoms of nitrogen and oxygen, producing cascades of secondary particles that lose energy as they pass downward. By the time anything reaches the surface, its energy has been dispersed across countless interactions. In effect, the atmosphere provides shielding equivalent to a dense barrier of material, comparable to a thick layer of water many meters deep. This is not an analogy. It reflects the actual protective value of the air above you. You are living at the bottom of a vast ocean of gas that quietly absorbs harmful radiation before it can reach you. At sea level, the yearly radiation dose from cosmic sources is extremely low, only a fraction of a millisievert. It is so small that it is less than the radiation you receive naturally from the ground beneath you. The moon offers no such protection. Cosmic radiation reaches its surface with full intensity. Galactic radiation alone can deliver hundreds of millisieverts over the course of a year during periods when the sun provides minimal shielding. During more active solar periods, this exposure decreases somewhat, but introduces another danger: sudden bursts of solar particles capable of delivering intense radiation over a short time. But periods of high solar activity introduce a different kind of danger: solar particle events. Sudden releases of protons and heavier ions from the sun can deliver intense radiation doses within just a few hours. A large event could expose an unprotected astronaut on the lunar surface to more than 1 sievert in a single episode. To understand what that means, a dose of 1 sievert delivered quickly is enough to trigger acute radiation sickness. Symptoms can include nausea, vomiting, and clear damage to the body's blood-forming systems. At higher levels, around 3 to 4 sieverts, the risk becomes increasingly fatal without advanced medical care. On the moon, that level of care does not exist. There are no fully shielded treatment facilities, no intensive care units, only the protection offered by a suit or a habitat, and whatever shielding mass they contain. Radiation risk must also be understood carefully, because it builds over time, rather than acting instantly in most cases. Even so, an astronaut spending a full year on the moon could receive a total dose roughly 150 to 200 times greater than someone living at sea level on Earth during the same period. Space agencies set strict lifetime exposure limits for astronauts in order to manage long-term cancer risk. However, these limits were developed primarily for missions in low Earth orbit, where spacecraft benefit from partial protection provided by Earth's magnetic field. On the lunar surface, that protection is completely absent. Earth's magnetic field, created by movement within its molten core, extends far into space and forms a protective region known as the magnetosphere. This invisible shield deflects charged particles from the solar wind, guiding many of them toward the poles where they produce auroras. It is something we never see directly, yet it is essential. Without it, the solar wind would gradually strip away the atmosphere, as it did on Mars long ago after that planet lost its global magnetic field. The moon never developed such a long-lasting magnetic shield. There are small, localized regions of residual magnetism in its crust, but they offer no meaningful protection on a global scale. The lunar surface remains fully exposed to both solar radiation and galactic cosmic rays, with no shielding from above or from the sides. This exposure has an additional consequence. When high-energy particles strike the lunar surface, they do not simply stop. They interact with the regolith, the layer of rocky soil, producing secondary radiation. Neutrons, gamma rays, and other particles are scattered upward, forming a reflected radiation field that rises from the ground itself. This means that an astronaut standing on the moon is exposed from 2 directions at once. Radiation arrives from above, and, at the same time, it is generated beneath their feet. No suit can completely eliminate this, because the radiation is not coming from a single direction. It surrounds the environment. This reflected radiation field is rarely discussed, yet it is one of the most subtle and challenging aspects of the lunar environment. It challenges the simple assumption that shielding only requires placing material between you and a single source. On Earth, if radiation arrives from above, the solution is simple. You step inside a building, the roof and walls absorb most of the incoming particles, and the problem is largely contained. On the Moon, the situation is very different. Primary cosmic rays still arrive from above, but when they strike the surface, they generate secondary radiation that emerges from below and from every surrounding direction. An astronaut standing on the lunar surface is, in effect, standing within a field of radiation. Shielding the top and sides of a habitat does not stop the neutrons and gamma rays rising through the ground. Protecting against that requires mass beneath the structure as well, which means either burying the habitat or elevating it on a platform with shielding underneath. Neither option is simple. Both demand construction capabilities that do not yet exist on the Moon. This radiation environment is not a single stream that can be blocked with a wall. It is a field that surrounds you, and even the ground beneath your feet becomes part of the source. In early 2026, NASA selected a new instrument payload designed to measure this combined radiation environment in detail for the first time. The fact that such measurements are still being developed more than 50 years after Apollo reveals something important. We still do not have a complete, direct understanding of the radiation conditions on the lunar surface. We rely on models, calculations, and limited data from earlier missions, but the full picture remains incomplete. If we set radiation aside for a moment, another challenge becomes immediately clear. Temperature. On Earth, you exist within a carefully balanced thermal system. The atmosphere traps heat, redistributes it through winds and oceans, and releases it gradually into space. The result is a relatively stable environment where temperatures in inhabited regions typically fall within a range that life can tolerate. Most human activity takes place within a narrow band of conditions, where the difference between a warm day and a cold night may be only a few dozen degrees. Your body manages this range with relative ease, adjusting through simple responses like sweating or shivering. The Moon operates under an entirely different system. Near the equator, surface temperatures during the lunar day can reach around 127 degrees Celsius. This is hotter than the boiling point of water and exceeds the limits of many industrial heating processes. At night, the same surface can fall to approximately -73 degrees Celsius. This is colder than any naturally recorded temperature on Earth, colder than the most extreme conditions in Antarctica. The total variation between day and night approaches 300 degrees Celsius. A single location on the Moon experiences a temperature swing far beyond anything found on Earth. What makes this even more challenging is the length of the cycle. A lunar day does not last 24 hours. It lasts about 29.5 Earth days. This means the surface remains in continuous sunlight for roughly 14 Earth days, followed by another 14 days of complete darkness. There is no rapid cycle to soften these extremes. There is no sunrise after a few hours of cold. When the sun sets on the Moon, it does not return for 2 full weeks. 14 days of uninterrupted darkness, during which the surface releases its heat directly into space with nothing to slow the loss. There is no atmosphere to hold warmth, no oceans to balance the change, no clouds to reflect heat back down. The surface cools continuously for 336 hours. Then, when sunlight returns, it shines without interruption for another 336 hours, heating the regolith with no atmospheric layer to diffuse or soften the intensity. Near the lunar poles, the situation becomes even more extreme. Because the Moon's axis is tilted by only about 1.5 degrees, some deep craters near the poles never receive direct sunlight at all. Not at any time of day, not during any season, not across any year. Measurements from orbital instruments have recorded temperatures in these permanently shadowed regions as low as -238 degrees Celsius. That is only about 35 degrees above absolute zero. Colder than the surface of Pluto, and among the lowest temperatures measured anywhere in the solar system. And yet, these are exactly the regions targeted by future mission, because such extreme cold may preserve water ice. a resource considered valuable for long-term exploration. But the thermal challenge is not just theoretical, it affects everything brought to the surface. Every material, every structure, every moving part, every seal, every wire. Every electronic system must endure these conditions. Materials expand when heated and contract when cooled. And a temperature swing approaching 300 degrees places enormous stress on any structure. Metals weaken over time. Seals fracture, and components begin to fail. Lubricants that function well at moderate temperatures can evaporate under intense heat or freeze solid in extreme cold. Electronics designed for Earth's environment stop working. Batteries lose efficiency in low temperatures and degrade when exposed to high heat. Solar panels can generate power during the long lunar day, but become useless during the equally long night, requiring either nuclear energy sources or large-scale storage systems to maintain operation. Apollo missions avoided these extremes by careful timing. They operated during the lunar morning, when temperatures were rising but had not yet reached their peak, and they departed well before night began. No Apollo crew ever experienced the lunar night. In fact, no human ever has. Now consider another layer of protection that Earth provides without effort: pressure. The atmospheric pressure at sea level is created by the weight of the air above you, and your body is deeply adapted to it. Your lungs expand against this pressure. Your blood vessels remain stable because internal and external pressures are balanced. Your sinuses, your ears, your eyes. Every cavity in your body exists in equilibrium with the surrounding air. Remove that external pressure, and the breakdown described earlier begins. The body becomes, in a very real sense, a pressurized system placed into an environment that can no longer support it. And this leads to an important point. Maintaining pressure is not just one requirement among many. It is the foundation for all the others. Without it, oxygen systems do not matter. Temperature control does not matter. Radiation shielding does not matter. Without pressure, survival ends within about 2 minutes. Maintaining pressure is not just one system among many. It is the foundation that supports every other requirement. On the moon, that foundation depends entirely on a barrier that may be only millimeters thick. The wall of a suit or the structure of a habitat separating life from vacuum. This is not comparable to wearing a coat in cold weather. A pressure suit must form a completely sealed environment around the body, while still allowing movement, work, and precise control. The person inside must be able to walk, bend, grip tools, and perform delicate tasks, all while enclosed within a rigid, pressurized system. The internal pressure of a modern spacesuit is far lower than Earth's atmosphere, typically around 4.3 pounds per square inch, compared to about 14.7 at sea level. This reduced pressure allows for some flexibility, but it comes with consequences. Astronauts must breathe pure oxygen beforehand to remove nitrogen from their bloodstream and prevent decompression sickness. Even then, the suit remains stiff. Every movement requires effort. Each step, each motion of the hand, each adjustment of a tool means working against the resistance of the suit itself. Apollo astronauts often described severe fatigue in their hands and arms after working on the surface, with some experiencing blisters and even losing fingernails from prolonged strain inside pressurized gloves. And all of these systems must function together, continuously, without interruption. Every layer of protection, every engineered solution must operate perfectly for the entire duration of a mission. On Earth, survival systems are separate and resilient. If the temperature drops, you seek shelter. If the air becomes poor, you move elsewhere. If radiation increases, you go indoors. Each problem has its own solution, and failure in one area does not immediately compromise the others. On the moon, everything is connected. The same suit that maintains pressure also supplies oxygen, regulates temperature, provides radiation protection, and enables communication. A failure in any one part can affect the entire system. The same is true for habitats. A single structure must provide atmosphere, manage temperature, generate power, recycle water, and handle waste. There is no secondary environment to retreat to, no natural backup. If the habitat fails, the suit becomes the only option. And if the suit fails, there is nothing. This complete dependence on engineered systems makes the moon fundamentally different from any place humans have ever lived. Even in the harshest environments on Earth, people survive in polar regions, in desert, at high altitudes. But in all of these places, the natural world still provides a baseline for survival. There is always air. There is always some level of pressure. There is always partial protection from radiation. On Earth, the challenge is to supplement what nature already offers. On the moon, nothing is provided. Every function must be recreated from the ground up, using systems that must not fail, in an environment that continuously works against them. And even something as basic as gravity, something we rarely think about at all, becomes part of that challenge. Gravity is what holds the atmosphere in place. It keeps water stable in liquid form on the surface. It maintains the pressure balance that allows your cardiovascular system to function, and it constantly loads your bones and muscles in ways that are essential for long-term health. On the moon, gravity is only about 1/6 of what you experience on Earth. This means a person who weighs 180 pounds on Earth would weigh roughly 30 pounds on the moon. At first, this seems appealing, even enjoyable, moving in long, slow arcs, lifting heavy objects with ease. The Apollo astronauts appeared to enjoy this experience, but reduced gravity has consequences that are not immediately obvious. Over time, those effects become significant, and they develop faster than most people expect. On the International Space Station, where astronauts live in near zero gravity, bone density declines at a rate of about 1 to 2% each month. Even with strict daily exercise routines, muscle mass can decrease by 10 to 20% within just a few weeks. The cardiovascular system also changes. The heart, no longer working against gravity to move blood upward, gradually weakens. Fluids shift toward the head, increasing pressure within the skull and leading to vision problems that have been observed in many long-duration astronauts. These effects occur in microgravity, where the gravitational load is essentially absent. The key question for lunar missions is whether 1/6 of Earth's gravity is enough to prevent or significantly reduce these changes. Current evidence suggests that it is not. A study conducted in 2024 examined mice living on the International Space Station under 3 different conditions. One group experienced microgravity, another was exposed to artificial lunar gravity, and a third group remained under full Earth gravity. The findings showed that bone loss observed in microgravity was only partially improved under lunar gravity. Signs of immune system decline were also only partially reversed. Changes at the genetic level related to bone and immune function were not fully corrected at that level of gravity. Another study found that while lunar gravity helped prevent severe muscle loss in certain muscles, it did not stop deeper changes in muscle structure. These changes are associated with reduced endurance and altered performance. A broader review of multiple studies concluded that partial gravity below roughly 40% of Earth's gravity appears insufficient to maintain long-term musculoskeletal and cardiovascular health. The Moon's gravity is far below that threshold. This suggests that astronauts living on the Moon for extended periods would likely continue to experience bone loss, muscle weakening, cardiovascular decline, and reduced immune function. Even though they would be standing and moving under gravity, the level of that gravity would not be enough. 1/6 of what the body requires is not a partial solution. It is a partial version of the same problem. And over time, those effects would accumulate, making it increasingly difficult to return to Earth's full gravity. Earth provides all of this for you, constantly and without effort. It surrounds you with air, shields you from radiation, and presses gently against your body with exactly the right force to keep your fluids stable, your lungs working, and your blood circulating. It holds you in place with the precise gravitational pull needed to maintain your bones, your muscles, your heart, and your sense of balance. It regulates temperature within a range your body can tolerate. It filters out harmful radiation from the sun while allowing visible light and warmth to reach the surface. And it does all of this automatically, continuously, without requiring anything from you. You have never needed to think about it. You have never needed to maintain it. You have never needed to rebuild it. On the moon, you must replace all of it. Every function, every layer of protection, every condition must be recreated at once, without interruption, and without any margin for failure. If those systems break, there is nothing to fall back on. And there is another aspect that is often overlooked. Even if every one of these challenges is solved, even if you create a habitat that is perfectly sealed, fully pressurized, properly shielded, and thermally stable, and even if it operates flawlessly for months, you still cannot remain inside forever. You still have to step outside. You must work on the surface. You must move across the regolith, handle equipment, collect materials, repair systems, and build infrastructure. Every time you leave the habitat, you exchange a controlled environment for the raw conditions of the moon. Each excursion becomes an exposure event. Radiation continues to accumulate. Dust begins to infiltrate suit systems. Thermal stress cycles through every component. The vacuum presses against the only barrier protecting you, waiting for the smallest failure. And beyond all of this lies something even more difficult to manage. A hazard that is not simply a result of distance from Earth, and not something that engineering has yet fully solved. The surface itself. The moon is not just empty, it is actively hostile. Its surface is made of material that damages everything it touches, both biological systems and mechanical ones, over billions of years. Constant impacts have transformed it into one of the most aggressive environments in the inner solar system. This material demands its own attention. Apollo astronauts, after spending only a few hours on the surface, warned that lunar dust could become one of the greatest obstacles to any long-term presence. Decades later, that concern remains unresolved. Up to this point, the focus has been on what the moon lacked. No air, no pressure, no magnetic shielding, nor natural temperature control. Those absences alone are enough to make it deadly. But the moon's danger is not limited to what is missing. The surface is covered in a substance that does not simply lie beneath your feet. It penetrates, scratches, corrodes, and contaminates everything it touches. It is not passive ground. It is an active threat, shaped over billions of years, becoming more dangerous with time. It has been shaped by a process that has no true equivalent on Earth. Lunar regolith is a layer of broken rock, mineral fragments, and fine dust that covers the entire surface of the moon. In most places, it extends several meters deep, and in older highland regions, it can reach depths of up to 15 meters. It was not formed by wind or water. It was created through constant impact. For billions of years, the moon has been struck by meteoroids of every size, from massive objects comparable to buildings down to particles smaller than grains of sand. Each collision shatters rock, crushes existing material, and produces a fresh layer of fragments that settles back onto the surface. Over immense spans of time, this continuous bombardment has ground the outer crust into a blanket of debris that covers everything. There is no exposed bedrock that has not been altered by impact. Every part of the surface is made from the remains of collisions that trace back to the earliest history of the solar system. On Earth, broken material does not remain sharp for long. Wind moves grains against each other, gradually smoothing their edges. Water dissolves sharp mineral surfaces. Chemical reactions alter and weaken structures. Cycles of freezing and thawing break materials along lines that tend to produce smoother fragments. As a result, dust and sand on Earth, while sometimes irritating, are made of particles that have been reshaped into relatively mild forms. Beach sand feels smooth. Desert dust is fine, but often rounded. Soil has been processed repeatedly by natural and biological activity over millions of years. In geological terms, it has been softened. Lunar regolith has never undergone that process. There is no wind to wear down sharp edges. There is no water to dissolve them. There is no chemical weathering. No biological activity. No erosion to reduce their intensity. When a micrometeoroid strikes the surface and breaks apart a mineral grain, the fragments retain every sharp edge created in that instant. Every jagged surface, every needle-like protrusion remains unchanged. Those particles remain exactly as they formed, for centuries, for thousands of years, even longer. With nothing to smooth or dull them, the result is a material composed of irregular, angular, and highly abrasive particles under a microscope. Samples returned from Apollo missions reveal shapes that resemble shattered glass, because in many cases, that is exactly what they are. The energy released during impacts can melt rock and silicate minerals, which then cool rapidly into tiny glass beads and coated fragments known as agglutinates. These glass-like fragments are among the sharpest and most abrasive elements of the regolith. They are not smooth or rounded. Instead, they exist as jagged, uneven shards with tiny hooks, barbs, and edges that catch onto nearly any surface they encounter. The wide range of particle sizes only makes this hazard more severe. Lunar regolith includes grains across an enormous spectrum, from coarse pieces several millimeters in size down to extremely fine particles measured in fractions of a micron. The smallest fraction, particles below about 20 microns, is classified as lunar dust. And this is where the greatest risk begins to emerge. Particles smaller than 10 microns are capable of penetrating deep into the human respiratory system. Those below roughly 2.5 microns can reach the alveoli, the tiny air sacs where oxygen exchange takes place. Lunar dust contains a substantial number of particles within both of these critical ranges. Some are even finer, measuring only a few hundredths of a micron, small enough to pass through biological barriers and interact directly with individual cells. On Earth, particles of similar size from industrial environments are linked to diseases such as silicosis, lung fibrosis, and increased cancer risk. Lunar dust shares many of the same physical traits as these harmful particles, and in some respects may be even more dangerous, because it has never been exposed to air or moisture that could reduce the reactivity of its surfaces. There is also another property that makes lunar dust uniquely problematic. It can become electrically charged. The surface of the moon is constantly influenced by two main sources of electrical charging. One is the solar wind, a continuous stream of charged particles, mainly protons and electrons, flowing outward from the sun at speeds of hundreds of kilometers per second. When these particles strike the surface, they interact with regolith grains, transferring charge and altering the electrical state of the surface layer. The second source is ultraviolet radiation from the sun, which carries enough energy to eject electrons from the surfaces of mineral grains through the photoelectric effect. During the lunar day, areas exposed to sunlight tend to become positively charged as electrons are removed, while regions in shadow collect negative charge from incoming solar wind particles. This creates a highly dynamic electrical environment where surface charge can shift dramatically over very small distances, especially near the boundary between light and shadow. This electrical behavior leads to a direct and important consequence. Charged dust particles are drawn to surfaces through electrostatic forces. They do not simply settle and remain still. They cling. They attach themselves to fabric, to visors, to metal structures, to seals and joints, to every exposed surface. And they do so with a persistence that simple brushing cannot easily remove. Apollo astronauts realized this almost immediately during their first moments on the surface. Dust covered nearly everything. It worked its way up their suits from the boots. It settled across their visors. It embedded itself deep into the woven fabric of the suit so completely that brushing could not fully remove it. When they returned to the lunar module and repressurized the cabin, the dust followed them inside. It drifted through the air. It coated control panels and equipment. It irritated their eyes. It entered their lungs. Harrison Schmitt, the geologist on Apollo 17, described symptoms similar to hay fever shortly after removing his helmet inside the module. He experienced nasal congestion, sneezing, and irritation that lasted for hours. Other crew members reported comparable effects, even though their exposure was brief, limited to the short periods between surface activity and departure. Medical evaluations conducted afterward showed signs of airway irritation, and one analysis suggested that lung function may have decreased by around 10 to 20% following exposure. These were highly trained, physically fit individuals experiencing measurable respiratory effects after only a few hours of indirect contact with lunar dust inside a controlled environment. The full toxicity of this material is still not completely understood, and that uncertainty is itself a concern. No human has ever experienced long-term exposure, so the biological effects over extended periods remain largely unknown. What we do have comes from laboratory studies. Using simulated lunar dust and the limited samples brought back by Apollo missions, these studies suggest a troubling picture. The particles are physically abrasive, capable of penetrating deep into lung tissue and causing inflammation through direct damage to cells. There is also evidence that the dust is chemically reactive. Fresh lunar particles, untouched by air or moisture, may produce reactive oxygen species when they come into contact with biological tissue. These molecules can damage DNA, trigger inflammatory responses, and contribute to cell death. A review published in 2022 outlined both known and potential risks, including lung scarring, chronic airway inflammation, irritation of sensitive tissues, and the possibility that these effects could be amplified when combined with radiation exposure. The researchers noted that the full range of health effects from long-term, low-dose exposure is still not fully understood, and they identified this as a major gap in planning for extended missions on the Moon. It remains unclear whether real lunar dust is more or less reactive than the simulated materials used in laboratories. Some findings suggest that the reactive surfaces of regolith particles may become neutralized relatively quickly when exposed to air and moisture inside a spacecraft. However, other studies indicate that this reactive state could persist for hours after initial exposure to an atmosphere. The actual level of risk may depend on several factors, including how quickly dust is carried into the habitat on suits and equipment, how effective filtration systems are at capturing extremely fine particles, and whether repeated exposures lead to cumulative damage that cannot be predicted from short-term studies. At present, there are no definitive answers, largely because the necessary long-duration experiments have never been conducted at the required scale. NASA clearly treats this as a serious and unresolved issue. In late 2025, the agency allocated more than $24 million to a research laboratory to develop an instrument designed to study charged lunar dust and near-surface plasma conditions at the Moon's south pole during a future mission. This instrument will measure properties such as particle charge, velocity, size distribution, and flux, along with electron density above the surface. Researchers have emphasized that building a complete understanding of the dust and plasma environment is essential for both astronaut safety and the reliability of mission equipment. The fact that such detailed measurements are still pending, more than half a century after Apollo, highlights how much remains unknown about the lunar surface. But the biological risk is only one part of the problem. Lunar dust is just as destructive to machinery. In some cases, its impact on engineering systems can be even more immediate than its effects on human health. During Apollo missions, dust contamination began degrading equipment performance within hours. Thermal control systems, which rely on specific surface properties to manage heat, were particularly vulnerable. Radiators must reflect most incoming sunlight while efficiently releasing heat into space. When dust settles on these surfaces, it alters those properties. The surface begins to absorb more solar energy while becoming less effective at radiating heat away. The result is a gradual buildup of excess heat. Data from Apollo showed that dust contamination could reduce radiator efficiency by as much as half. During short missions, this was manageable. Over longer periods, it could become a serious threat to both equipment and crew safety. Seals and moving components experience similar problems. Fine abrasive particles work their way into joints, bearings, and interfaces, acting like a grinding compound. This accelerated wear, damaged surfaces, and weakened seals that were critical for maintaining pressure. Mission records from Apollo contain numerous accounts of dust interfering with equipment, jamming mechanical systems, and degrading the performance of optical instruments. Camera lenses became scratched and clouded over time. Suit joints grew stiff as fine dust settled into their bearings. Equipment that had been carefully designed and tested in clean conditions on Earth encountered entirely new failure modes within just hours of exposure to lunar regolith. The laser retroreflectors placed on the surface during Apollo missions offer a striking long-term example. These instruments, made of precisely aligned reflective elements, were deployed to allow laser-ranging measurements from Earth. They require no power, have no moving parts, and simply return incoming light back toward its source. They have remained in use for more than 5 decades. Yet over that time, the strength of the reflected signal has declined by an order of magnitude. In some cases, by as much as 100 times. The leading explanation is the gradual buildup of dust on their surfaces, slowly degrading their optical performance. These are among the simplest devices ever placed on the moon, passive systems with no mechanisms to fail, and still, dust has reduced their effectiveness dramatically over time. It raises an important question about what happens to more complex systems. Tall solar panels, windows, sensors, and any surface that depends on precise optical or thermal properties during long-duration missions. Now consider the environment that produces and constantly redistributes this dust in ways that have no equivalent on Earth. The Moon has no atmosphere to slow incoming material. Micrometeoroids, tiny fragments of cometary and asteroidal debris, range from particles smaller than grains of salt to pieces the size of small stones. They strike the lunar surface at extremely high speeds, typically between 10 and 70 kilometers per second. On Earth, most of these particles never reach the ground. The atmosphere slows them down and burns them up. The streaks of light seen in the night sky are small grains disintegrating high above the surface. On the Moon, those same particles arrive at full velocity. Even a fragment with very little mass, moving at tens of kilometers per second, carries energy comparable to a projectile. When it impacts the surface, it creates a crater many times its own size and ejects a spray of high-speed debris in all directions. This process is continuous. The flow of micrometeoroids at the Moon's distance from the Sun is steady and predictable. Every square meter of the surface is struck over time, and the cumulative effect is significant. It is not like rainfall. It is more like standing in a vast open field where small impacts occur somewhere nearby every few seconds. The chance of a direct hit on a specific object at any given moment is low, but over months or years, the probability that something will be struck increases. And without an atmosphere to provide warning or slow incoming particles, the only real protection is physical shielding. You cannot detect a particle the size of a millimeter moving at 20 kilometers per second until it has already struck something. The debris produced by these impacts also plays a major role in spreading dust across the surface. Each micrometeoroid collision sends a spray of regolith fragments outward along ballistic paths. Some of these particles travel significant distances before eventually settling again. This creates a constant, faint rain of secondary dust across the lunar surface. It is a process that has continued for billions of years and will not stop. Any object left on the Moon gradually accumulates this additional layer of material, on top of the dust already clinging to it through electrostatic forces. These two processes reinforce one another. Electrostatic attraction keeps dust attached once it arrives, while continuous impacts deliver new particles. Over time, every surface becomes progressively more contaminated, not cleaner, and there is no natural mechanism to reverse this buildup. Rocket activity introduces another serious complication. During landing and takeoff, engine exhaust interacts directly with the regolith. Without an atmosphere to contain or slow the flow, particles are blasted outward at high speeds. Observations from past missions have shown that exhaust can accelerate regolith to velocities of hundreds or even thousands of meters per second. sending particles far from the landing site. These high-speed grains can effectively sandblast nearby equipment, habitats, and instruments. If future missions establish permanent structures near landing zones, each new arrival could pose a risk to everything already in place. Addressing this would likely require specially prepared landing surfaces made from processed regolith, which in turn demands complex construction efforts before routine operations could even begin. Taken together, these dust-related effects create a pattern of degradation unlike anything encountered on Earth. In terrestrial environments, equipment typically wears down through oxidation, moisture exposure, biological growth, and mechanical use. These processes are well understood, and maintenance strategies can be planned accordingly. On the Moon, degradation follows a very different path. Surfaces are worn down by ultrafine glass-like particles, subjected to extreme temperature cycles of hundreds of degrees over the course of each long day and night, exposed to constant radiation, coated with electrically charged dust, and struck by micrometeoroids capable of damaging even robust materials. All of these processes occur at the same time, continuously, and their effects accumulate. No testing facility on Earth can fully reproduce this combination of conditions. Engineers can simulate vacuum, temperature variation, dust exposure, or radiation individually, but not all of them together in the exact way the lunar environment presents them. This means that predictions about how equipment will perform on the Moon remain uncertain. True reliability can only be understood after systems operate there over long periods. And when something fails on the Moon, the consequences are fundamentally different from failures on Earth. There are no supply chains, no repair centers, no immediate replacements. Everything must be brought from Earth, and every failure carries a cost that cannot be easily resolved. Everything on the Moon must be transported from Earth, at a cost that can range from roughly $10,000 to $50,000 per kilogram. Depending on the mission design, a damaged seal is not a minor issue. It becomes a potential emergency, requiring either a spare component that was delivered at enormous expense or an improvised solution using whatever limited materials are available. Apollo astronauts, even during their short stays, understood this reality very clearly. In their post-mission reports, one issue appeared again and again: dust. It was not a small inconvenience or a cosmetic problem. It was a serious operational hazard that affected nearly every aspect of working on the surface. Gene Cernan, the last person to walk on the Moon, described lunar dust as one of the most significant obstacles for future missions. Some astronauts went even further, suggesting that dust could become the single greatest barrier to maintaining a long-term human presence there. These conclusions came from missions that lasted only about 3 days, conducted in relatively stable equatorial regions during the lunar morning. The polar regions targeted by modern missions are colder, darker, and far less understood. Yet the dust remains the same: charged, abrasive, and persistent. The same material that interfered with equipment and seals decades ago. More than 50 years have passed since those warnings were first given. Engineering has advanced significantly since then. Technologies such as electrostatic dust removal systems, which use oscillating electric fields to repel particles, have been tested in space and shown promising results under controlled conditions. Modern suit designs include improved sealing mechanisms, more resistant fabrics, and modular components that can be replaced if contamination occurs. Habitat concepts now incorporate specialized airlock systems intended to keep contaminated suits outside, reducing the risk of dust entering living spaces. Advanced filtration systems are also being developed to capture the extremely fine particles found in lunar regolith. However, none of these solutions have yet been fully proven on the Moon itself. None have operated for extended periods under real lunar conditions, where charged dust, extreme temperature cycles, and continuous micrometeoroid impacts all occur together. They are successful in controlled environments, but still waiting to be proven in the harsh reality of the Moon itself. one of the most unforgiving testing grounds in the inner solar system. The gap between results achieved on Earth and actual performance on the Moon is exactly where past assumptions have failed. The Moon is not an empty platform waiting for human activity. It is an environment that actively resists human presence at every level. From microscopic chemical reactions on dust particles to the high-speed paths of debris thrown out by impact, it works against anything brought to its surface. It wears down materials, it coats exposed systems, it grinds moving parts. It charges particles and causes them to cling where they should not. Over 4.5 billion years, this surface has been shaped by constant, unprotected bombardment into one of the most abrasive, adhesive, and invasive materials found anywhere humans have explored. Unlike hazards such as vacuum, radiation, or temperature, which can in principle be reduced by building stronger barriers between people and the environment, dust cannot be completely isolated. The mission itself requires interaction with the surface. Every time an astronaut steps outside, contamination begins. Every return inside carries the risk of bringing that contamination with them. This is what makes the Moon fundamentally different from a place that simply lacks protection. It is a place that actively pushes back, and it does so with a persistence that no human timeline can outlast, because the processes that create and move lunar dust never stop. They existed long before humans arrived. They continued during Apollo. They will continue through Artemis. And they will persist for billions of years after humans are gone. The dust does not weaken. It does not disappear. It is the surface itself. And the surface is inseparable from the mission. So the question is no longer whether these conditions can be endured for a few hours. Apollo already answered that. The real question is whether they can be endured for months, for years, for any length of time that could truly be called a return. And to answer that, we have to face what returning actually means. There is a simple conclusion one could draw from all of this. The Moon is dangerous, so do not go. But that would miss the point entirely. Human beings can reach the Moon. That was proven in 1969, and confirmed again multiple times afterward. The challenge was never about getting there and surviving briefly. The real question, the one often hidden behind the phrase going back, is what happens when we try to stay. Apollo was an act of arrival. Each mission followed the same core structure: launch, travel, land, spend a limited amount of time on the surface, gather samples, then leave and return to Earth. The entire system was designed around short duration. The lunar module carried enough oxygen, water, and power for a maximum stay of about 75 hours, and most missions used far less. The command module in orbit held just enough supplies for the journey. With carefully calculated safety margins, nothing was reused. Nothing was left behind in working condition for future crews. Every mission was a closed system, beginning at launch and ending with a return to Earth. The Moon was not treated as a place to live. It was a point of contact, something to reach and then leave behind. Like touching a hot surface briefly, just long enough to prove it could be done. This approach allowed Apollo to succeed because it avoided the long-term challenges entirely. Radiation exposure over a few days remained within acceptable limits. Temperature conditions during a single lunar morning could be managed with available technology. Dust, while problematic, remained a short-term issue rather than a persistent threat. Bone and muscle loss over a period of about 3 days in reduced gravity was minimal. Life support worked because all necessary supplies could be carried. System reliability worked because everything only needed to function for a short time. Apollo succeeded not by overcoming the Moon's dangers, but by limiting exposure to them. The missions were so brief that the environment never had time to fully reveal its effect. Any meaningful return to the Moon requires something very different. It requires staying, and staying does not increase difficulty in a simple, gradual way. It increases it dramatically, because the Moon's hazards build on each other over time. Take radiation as an example. Exposure does not reset each day. It accumulates. A short mission keeps total exposure within safe limits. Extend that duration to a month, and it becomes a serious concern. Extend it to a year, and it approaches or exceeds what is considered acceptable for an entire astronaut's career. And this does not even include the impact of a single solar event adding to the total. The issue is not only the amount of radiation, but permanence. Every dose received becomes part of a lifetime record. It cannot be undone. It does not heal or reverse in the way other physical effects might. The damage to DNA builds up over time in ways that may not become visible for many years. An astronaut who spends several months on the lunar surface could return appearing completely healthy, only to develop radiation-related illness decades later. And every moment spent on that surface, every high-energy particle absorbed, becomes part of that long chain of cause and effect. This delayed impact makes radiation one of the most subtle and dangerous hazards on the Moon. Dust leaves visible damage. Temperature cycles place stress on materials in ways that can be measured, but radiation works quietly, invisibly, on a timescale that extends far beyond the mission itself. The only meaningful protection is shielding. And effective shielding requires mass. Metal walls provide some defense, but they cannot fully block the most energetic cosmic rays, which can pass through several centimeters of solid material. The most practical approach remains covering habitats with several meters of regolith, but achieving that requires heavy equipment and construction capabilities that must already be in place before crews arrive. Until such systems exist, early missions will operate under exposure levels that would never be considered acceptable in any Earth-based workplace. Thermal management over long durations presents another challenge. These extreme temperature swings are not isolated events. They repeat over and over, placing continuous stress on every exposed structure. A habitat must both release heat during the long lunar day and retain it during the equally long night, switching between these opposing demands every 2 weeks. The strain on materials is significant. Components expand and contract, connections shift, seals gradually weaken. Each cycle introduces small amounts of damage that accumulate over time. On Earth, buildings are designed to handle seasonal temperature changes across relatively moderate ranges. On the Moon, structures must endure swings of hundreds of degrees every single cycle. Over the course of a year, this means repeated exposure to extreme conditions that test every joint and every surface. There is no direct precedent for this. The materials, design, and systems required must be developed and validated in ways that go far beyond standard engineering practices. Dust becomes an even greater issue over extended periods. Every activity outside the habitat brings regolith back toward the living space. Even with advanced airlock systems designed to keep contaminated suits outside, some transfer is unavoidable. Particles cling to tools. They attach to containers. They build up on mechanisms themselves, slowly degrading performance over repeated use. Once dust enters the habitat, it becomes extremely difficult to remove. There is no simple way to expel it without also losing the atmosphere. Over time, it accumulates, becoming a persistent and unavoidable contaminant within the living environment. Filtration systems must continuously capture particles at extremely small scales, even down to submicron levels. And those filters must be replaceable because they will inevitably become saturated. The long-term respiratory risk for crew members depends on how much dust accumulates inside the habitat over time, a variable that has never been directly measured in a real lunar environment, simply because no long-duration habitat has ever existed there. Now consider how gravity adds to this challenge over time. A crew arriving after a 3-day journey in microgravity already begins in a slightly weakened condition. The Moon's gravity provides some physical load, but current evidence suggests it is not enough to fully preserve muscle strength, bone density, and cardiovascular performance. A crew staying for 30 days would likely experience measurable changes in bone density and muscle function. Extend that stay to 6 months, and the effects become more serious. Then comes the return to Earth, where re-entry subjects the body to forces several times stronger than normal gravity, acting on individuals who have adapted to a much lower gravitational environment for half a year. This transition has never been fully tested. No human has spent extended time in partial gravity. Most available data comes from microgravity environments, which behave differently. Studies on Earth suggest that reduced loading leads to partial physical decline. But the exact progression under 1/6 gravity over many months remains uncertain. To understand what all these combined hazards mean in practice, it helps to imagine a 30-day mission on the lunar surface. Not the idealized version, but the one shaped by real constraints and conditions. On the first day, the crew lands. The descent engine blasts regolith outward at high speed, sending particles across the surrounding area and potentially damaging nearby equipment. The crew activates the habitat, checks structural integrity, pressurizes the interior, and begins verifying that every life support system survived the journey and landing without failure. Outside, the charged dust thrown up by the landing has already started to settle across every exposed surface, including the solar panels that the habitat depends on during the long lunar day. By the third day, the first excursions begin. The crew exits through the suit lot, steps onto the regolith, and starts surface operations. Within minutes, dust begins to cover their suits from the boots upward. It embeds into the outer layers of fabric. It sticks to the visor, slightly dimming visibility. It works its way into the joints of the gloves, adding resistance to even the smallest finger movements. When they return, the suits remain outside, but the tools come back in. Sample containers come inside. Anything that touched the surface carries particles with it. The filtration system starts working immediately, but the finest particles, the smallest glass-like fragments, push even advanced filters to their limits. The crew notices a faint metallic scent that was not present before. It is the same smell reported during earlier missions, the result of reactive dust coming into contact with air and moisture for the first time. By the 7th day, routines are established, but the accumulated effects begin to show. Radiation monitors display a steady increase. The total exposure already matches what would normally take months on Earth, compressed into a single week. The thermal radiators on the exterior begin to show early signs of reduced efficiency due to dust buildup, forcing the system to work harder to manage heat during the extended daylight period. The crew maintains a strict exercise schedule, but the reduced gravity is noticeable. Movement feels effortless, almost light. But that ease is misleading. The body begins to adapt. The heart works less against gravity. Bones experience less stress with every step. Gradually, the body starts reducing the strength it no longer believes it needs. By the 14th day, the sun sets. For the first time, the mission enters lunar night. Temperatures begin to fall, and they continue to drop without interruption for 2 full weeks. The solar panels stop producing power. Every system now depends on stored energy or alternative power sources to sustain life support. Heating, communication, and operations through 336 hours of complete darkness. The thermal system shifts completely, moving from releasing heat to conserving it. The structure of the habitat begins to contract as external temperatures drop far below freezing and continue falling. Seals that expanded during the long daylight period now begin to tighten. The crew can hear subtle sounds, the structure adjusting under stress. Sounds no engineer has ever truly experienced in a real lunar habitat, because no habitat has yet endured a full night cycle on the moon. By the 21st day, the crew is deep into the lunar night. The sun has been gone for a week. Outside, the landscape is faintly illuminated only by distant Earth light and stars, if the terrain even allows it. Inside, systems continue to function, but all are operating under conditions that have never been tested for this long beyond controlled environments. The air filtration system has been running without pause for 3 weeks, processing whatever dust entered during earlier surface activity. Radiation exposure continues to rise, unaffected by the absence of sunlight. Cosmic rays do not follow a day-night cycle. The readings increase whether the surface is bright or dark. If a solar particle event were to occur, the crew would remain inside and rely entirely on the shielding provided by the habitat walls. There is no quick escape. Preparing for departure takes time. Earth is still 3 days away. A solar storm can deliver its full impact in a matter of hours. By the 30th day, sunlight returns. The habitat endures the transition back to daylight. The seals hold. Power systems resume collecting energy from the sun. The crew prepares to leave, completing a full month on the lunar surface. One complete cycle of day and night. And by that point, every system has been affected, every measurable aspect of the mission, from the crew's physical condition to the performance of equipment, has been altered by the combined influence of radiation, extreme temperature variation, dust exposure, and reduced gravity, all acting continuously over 30 days. This is not a worst-case scenario. It is the baseline. This is what a single month looks like when everything works as intended, when no unexpected failure occurs, when no major solar event strikes, when no critical component is damaged, when every system performs exactly as designed. This is the best-case scenario, and even in this form, it is demanding enough that no space agency has yet fully built and certified systems capable of carrying it out. Every one of these hazards does not exist in isolation. They interact, amplify, and compound each other. Radiation damage becomes harder to manage in a body already weakened by reduced gravity. Dust becomes more harmful to lungs that may already be affected by changes in immune response. Thermal cycling slowly degrades the very seals that protect against vacuum, and maintaining pressure is the foundation for all survival systems. A radiator coated in dust struggles to release heat, causing systems to overheat during the long lunar day. A power system relying on solar panels, already degraded by dust accumulation, may not sustain full operation when the transition to lunar night begins. One issue feeds into another. Failures do not occur alone. They cascade. Each individual challenge is severe. Together, they form a level of difficulty that no single test environment on Earth can reproduce, because no place on Earth combines all of these stresses at once. This is why the timeline and structure of modern lunar programs have shifted so much. What matters is not the exact schedule or individual delays, but the pattern behind them. Each delay has been tied to a specific technical or physical problem that proved more complex than expected. And these challenges so far involve only the journey itself, the rockets and spacecraft that carry crews to the moon and back. They do not yet fully include the systems required to operate on the surface. The landers, the suits, the habitats, the power networks, the dust mitigation technologies. All of these must function perfectly in an environment that has never been tested at full operational scale. They represent an entirely separate layer of complexity beyond the already difficult task of reaching the moon. The challenges of getting there are significant. The challenges of staying are even greater. And those surface systems have yet to be proven under real conditions. These delays are not failures. They are signals. Each one reveals something important about the gap between expectation and reality. Consider the heat shield. During a recent uncrewed mission, the spacecraft re-entered Earth's atmosphere after traveling to the moon. The protective material designed to burn away in a controlled manner behaved differently than predicted. Instead of eroding smoothly, parts of it broke away unevenly. The crew module remained safe. The spacecraft survived. But the difference between expected and actual behavior showed that the models were incomplete. And that gap, between what we think will happen and what actually happens, is exactly where the moon becomes dangerous. And when models fail to accurately predict heat shield behavior at speeds of around 25,000 miles per hour, they cannot be trusted with human lives until the difference is fully understood. That investigation lasted more than 2 years. It required extensive ground experiments, detailed simulations, and eventually led to the conclusion that the current shield was safe enough for crewed missions, but that future designs would need significant revision. This is a heat shield, one of the most essential elements of any spacecraft returning from beyond low Earth orbit. And still, it took years to understand why it behaved differently during a single re-entry from lunar distance. Even battery systems aboard the European service module encountered failures during vibration testing, forcing redesign, replacement, and full recertification. These are not advanced or experimental systems. Batteries and heat shields are among the most fundamental technologies in spaceflight. Yet the specific demands of lunar-class missions revealed weaknesses that standard testing on Earth had not exposed. The landing system presents an even greater challenge. The Apollo lunar module was designed for a very different type of mission. Artemis missions aim to land near the lunar South Pole, an area defined by extreme terrain. Steep crater edges, scattered boulders, permanently shadowed regions lying next to sunlit ridges, and uneven slopes that create serious landing risk. Lighting at the South Pole introduces a unique hazard. Shadows are not temporary, they are permanent features. Some extend for kilometers, covering entire crater floors in darkness that has remained untouched by sunlight for billions of years. A landing system approaching this environment must identify a safe landing zone while descending, distinguishing between flat ground and hidden obstacles. Orbital maps can resolve details down to about 1 meter, but they cannot reveal what lies inside permanently shadowed regions. Terrain that appears safe from above may conceal hazards that only become visible when the lander is already committed to landing. The human landing system being developed for these missions represents a completely new class of vehicle. It is far larger than the Apollo lunar module and depends on orbital refueling before it can even begin its descent. This process requires multiple launches and the transfer of cryogenic fuel in orbit at a scale that has never been demonstrated before. This is not a simple extension of past technology. It is an entirely new capability that must be built, tested, and proven before any crew can safely reach the surface. None of these challenges are impossible, but all of them are extraordinarily demanding. The difficulty is not mainly political, financial, or organizational. Even though those elements do play a role, the true challenge is physical. It comes from the moon itself, from the vacuum, the radiation, the violent temperature swings, the dust, the low gravity, and the constant hostility of an environment that does not adapt to human needs. The engineers working on Artemis are not failing. They are facing reality, and that reality is far more demanding than the familiar image of the moon ever suggested. This leads to the central realization behind everything we have explored. The reason returning to the moon is so difficult is not because it is far away. It is only a few days of travel. A short journey by the standards of space. The real reason is that the moon is close, and still this extreme. That combination challenges human intuition. We are used to associating danger with distance. The deep ocean feels dangerous. Antarctica feels dangerous. Mars feels dangerous. Deep space feels dangerous. Distance and risk are naturally linked in the human mind. But the moon breaks that pattern. It is right there. You can look up and see it with your own eyes. You can point to it. It feels close, almost familiar, and yet, its surface is so unforgiving that even after decades of technological progress, we still do not have fully proven systems for long-term human presence. This is not a failure of technology. It is a revelation about the nature of space itself. The moon is the nearest major world beyond Earth, the closest destination of real substance, the place that should, in theory, be the easiest to reach and remain on. And yet, it demands some of the most advanced engineering ever created just to allow a handful of people to stand there for a short time. If this is what the closest world requires, then what does that imply about everywhere else? If the nearest destination beyond Earth is this unforgiving, then expectations about Mars, about the asteroid belt, about the distant moons of the outer planet, must be reconsidered. These are not simply challenges of building larger rockets or waiting longer. They represent environments that may be even more demanding, in ways we are only beginning to understand. The moon does not answer that question gently. It answers by destroying anything exposed to it, slowly and relentlessly, through processes that act on every level, from microscopic interactions to large-scale forces. It shows that even a distance of around 239,000 miles, even a journey of only a few days, even a world we have already walked on, is enough to reveal how dependent human life is on Earth's protection. You do not need to travel to Mars to understand how unforgiving space can be. You do not need to reach distant moons or explore the outer edges of the solar system. Everything about the relationship between human life and space can be learned by going to the nearest world and attempting to remain there for a short time. The moon is not too distant. That is the uncomfortable truth. It is close enough that its lesson cannot be ignored. If it were farther away, it would be easy to assume that its dangers come from distance alone. We might believe that nearby places are easier, that extreme risks only exist far out in space. But the moon does not allow that assumption. It sits close to Earth, visible and familiar. Yet its environment is harsh beyond intuition. Its surface temperatures shift in ways that would damage most equipment within a few cycles. Its radiation exposure increases long-term health risks within months. Its dust interferes with breathing, damages machinery, disrupts optics, and affects thermal systems at the same time, without pause. Its gravity allows the body to weaken even while moving and working. Its vacuum would end life within minutes if protection fails. And all of this exists on the closest destination beyond Earth. This is the place meant to prepare us for something more difficult. The honest way to understand returning to the moon is not to see it as impossible. It is achievable. Past missions prove that reaching it is within human capability. Future missions will demonstrate that it can be reached again with modern technology. Engineering will continue to improve. Dust mitigation will advance. Radiation protection will become more effective. Thermal systems will be refined. Habitats will be constructed. Power systems will be deployed. Humans will almost certainly walk there again. But each of these achievements comes at a cost: time, resources, effort, and risk, all far greater than what the phrase "going back" suggests. Because going back to the moon does not mean returning to a familiar place. It does not mean revisiting something known and manageable. It means entering one of the most hostile environments humans have ever attempted to operate in for extended periods. At a place where every condition for survival must be created from nothing, where each system has to operate continuously in an environment that slowly wears it down, where the line between life and failure is measured in the thickness of a suit or the reliability of a filter, and where the only way back is a 3-day journey across empty space to the only world known to support human life naturally. The moon does not care that it is nearby. It does not care that humans have visited before. It does not respond to schedule, budget, ambition, or nostalgia. It is a world without air, without magnetic shielding, without stable temperatures, without breathable atmosphere, without sufficient gravity, and without any form of natural protection. Its surface is covered in material that harms both human lungs and mechanical systems with equal indifference. It is exposed to radiation that the human body cannot endure for long. It shifts between temperatures that would destroy most materials used in everyday life. And all of this exists just beyond our planet. That closeness is not comforting. It is the most important detail of all. The moon is near enough to see with the naked eye, near enough to reach in a matter of days, near enough that communication can happen almost instantly. And yet, it remains harsh enough to demand the highest level of engineering just to support a short, sustained human presence. This is what the moon reveals about humanity's place in space. Not simply that space is vast or distant, though it is. Not only that, other worlds are unfamiliar, though most are, but that even the nearest, most familiar destination beyond Earth is fundamentally incompatible with human life. Remaining there, even briefly, requires solving challenges that decades of progress have not fully overcome. This is the difficult truth. Not that exploration should stop, not that reaching the moon is impossible, but that returning in any meaningful way forces us to face how fragile human survival really is beyond Earth. The moment we leave the atmosphere of the only planet that has ever sustained us, everything changes. The footprints left during earlier missions are still there, untouched and preserved in the regolith. No wind has disturbed them. No rain has worn them away. No life has altered them. They remain in silence, in vacuum, under cycles of intense heat and cold, on a surface that charges its own dust and slowly wears down everything it meets. They will remain there for millions of years, long after the civilizations that created them have risen, faded, and risen again. Because nothing on the moon truly changes. Nothing erodes. Nothing softens. Nothing breaks down through the quiet, natural processes that Earth uses to reclaim what is left behind. That is not preservation. It is a signal. The moon does not erase those footprints because it has no capacity for gentleness. It has no air to carry sound, no water to support life, no soil where anything can grow. It is a world locked in the aftermath of violence, shaped by impacts, exposed to radiation, cycling endlessly between heat and cold, completely indifferent to how it appears from a distance of hundreds of thousands of miles. We will return. The engineering will reach that point. The suits will become more capable. Habitats will be constructed. Dust will be managed. Not perfectly, but well enough to allow crews to operate for weeks, and eventually for longer periods. Radiation will be reduced through shielding, structure, and careful planning. Thermal extremes will be handled by materials and systems designed for conditions more severe than anything engineers have faced before. All of this will happen because a species that once looked up at the moon and chose to go there is not one that stops when the challenge becomes greater than expected. But when we return, we must do so with clarity, not the moon shaped by memory, not the version captured in photographs and flags, not the calm, familiar disk in the night sky, the real moon, the one that removes every layer of protection your planet provides, the one that wears down every system you bring, the one that does not ease a single danger simply because the journey to reach it is short, the moon that shows, without ambiguity, that closeness does not mean safety, that familiarity does not equal understanding, and that even the nearest world beyond Earth is already harsh enough to reveal how fragile human life becomes the moment it leaves home.